Welcome to Category Theory, the Beginner's Introduction. I am Martin Codrington, and this is Lesson 1, Video 4 of 6. Last time, we looked at composition. We saw that the theory said that whenever we have arbitrary maps, f from A to B and g from B to C, we can complete the figure by forming the composite g following f. We said we could rename the composite if we desired, but that since there could be many maps A to C, we had to explicitly state one of two things. 1, we had to say that R equals G following F, or 2, that the diagram commutes. Today we will see more of commutative diagrams when we discuss the final 3 parts of the definition: the identity arrow, the identity laws, and associativity. In set, the identity arrow is a map that takes each element of the set to itself, i.e., for an arbitrary A in A, 1A of A is equals to A. As an example, consider the following abstract set A. Here is a mapping graph of the identity arrow, but since the domain and codomain are the same set, we can redraw the diagram like this. These types of morphisms, in which the domain and codomain are the same set, are called endomorphisms. We will study these in great detail in the future, as they form a category of their own, sets with an endomorphism, which are basically discrete time dynamical systems or automatons. This is my favorite category for data analysis and number theory. It's especially great for expressing non-mathematical things in a way that will allow you to calculate a precise mathematical relationship, especially for geometric data. More of that in the future, but back to 1A. On the surface, this looks rather uninteresting, doesn't it? But believe me when I tell you that the identity arrow will factor into, or rather cancel out of, most of your category theory formulations. It is probably the arrow you will want to produce the most. Any two functions that produce an identity arrow when composed have one of 3 special relationships, but that's the topic of lesson 2. We will continue this discussion then. You may have a question. Why is this the identity arrow in S? We will see that it satisfies the identity laws in this video, and that proves that it is a valid identity arrow, but as to why it is the identity arrow, we will have to wait until video 6 of this lesson to see. There we will derive it using a new and powerful tool we'll learn in the next video. So, back to music S, we officially have 3 more arrows. Let's look at the identity laws now. Suppose we have a category with 2 objects A and B. Since the theory tells us that every object has a special identity arrow, let's draw a representation of our category with these 2 objects and arrows. Now suppose we have a map F from A to B. Let's draw that in the diagram, but where? There are 1, 2, 3, 4 places we can draw it. Well, let's draw it at the top, the bottom, and one of the diagonals. I'm going to choose this one, but both choices will create the same diagram. The identity law can now be restated as follows. In any category, this diagram must commute. Remember that for a diagram to commute, all paths between 2 objects must be interpreted as the same arrow. So this path, 1B following F, must be the same as this path, F following 1A, which must be the same as this path, F. And that's exactly what the identity laws say. That F following 1A is equal to 1B following F is equal to F. Well, does this make sense? Let's suppose that F of A0 equal B0. So F following 1A of A0 is equals to F of A0, which is equals to B0. And 1B following F of A0 is equals to 1B of B0, which is equals to B0. So it makes sense. Okay, here's a quick glimpse into our future. Remember I said that these objects, a set with an endomorphism, where the arrow has the same object as the domain and codomain, form a category of their own right? Well, each set equipped with their identity arrows is an object in this category. If we take all the objects in S and make them into an object in sets with an endomorphism, with the identity arrow as the endomorphism, then we want to say that any function f from A to B that was a function in S is still a function f A1A to B1B in sets with an endomorphism, right? That only makes sense. But what if we replace 1A with any endomorphism alpha and 1B with any endomorphism beta? Then what would be a valid map in this category? Well, let's take the identity laws and replace the functions there too. F following 1A equals 1B following F becomes F following alpha equals beta following F. And that's exactly the rule that a valid map f from A alpha to B beta must follow in this category. So S can be viewed as a special subcategory of sets with an endomorphism, one in which the endomorphisms are the identity arrows, i.e. each state is a loop. No states are accessible from any other state. All states are isolated, as are all elements in a set. Actually, the category of permutations, which are sets with an automorphism, which is an isomorphic endomorphism, is a subcategory of sets with an endomorphism. So, set is a subcategory of sets with permutations. We will see a lot of this, how categories of structured sets arise from constructs in set. And since the identity law is defined for any category, we can make categories of categories with an endomorphism. The structure of these categories will differ from category to category. This is extremely useful for many things, but you can also make dynamical systems or permutations with any object as the state, because you can form sets whose elements are objects from any category, even dynamical system of permutations themselves. These categories are a direct result of the simple axioms. And this really is the point of category theory. It's not that it simply gives you a tool to connect all of mathematics, but it shows you how one construct naturally arises from the other. More of this in the near future, but back to the present. This arrow, the identity arrow, will often factor into proofs this way. If you have, for example, an f following g following h equal to k, then you can show that g following h is equals to 1a, then you can conclude that f is equal to k. We'll see many examples of similar cancellation properties between certain types of functions in the next lesson. And that's it for the identity laws as far as the definition of a category goes. Let's move on to the last part of the definition, associativity. The associative law says that composition of arbitrary maps, f from A to B, g from B to C, and h from C to D is associative, i.e., the following relations hold. H following g following f is equals to h following g following f. Just saying it out loud makes it seem kind of obvious, doesn't it? But guess what we're going to do? Yes, construct a commutative diagram that illustrates this axiom. Diagrams are the core of category theory. We need to get used to reasoning with them. We have four objects, A, B, C, and D, with arrows f from A to B, g from B to C, and h from C to D. Well, we know from the composition axiom that whenever we have a partial triangle, we can complete it with the composite. So at the top, we can form g following f, and at the bottom, we can form h following g. The associativity law says, you guessed it, that this diagram must commute. We have three paths A to D, h following g following f, h following g following f, and h following g following f. And they all must be interpreted as the same map. Let's look at an example. Let's say we have the following sets and the following arrows. Here's an exercise. Pause the video and draw the mapping graph. From there, it'll be obvious that it doesn't matter where you stop in between. All that matters is where you start and where you end. But I would also like you to explicitly calculate h following g and g following f, and then show that the law holds. And that's it. We've finished with the definition of set. We've discussed the objects, arrows, the identity arrow, composition, associativity, and the identity laws. This is what we'll need to do whenever we're defining any category. Prove that our objects and arrows follow these laws. Our proofs have been informal for S, but that's okay because I think these rules were obvious in this category. When we get to defining the 15 or 20 categories we will most often use, we will have tools to be more formal in our proofs. But honestly, we're not going to need proofs because many of our categories we will construct from S in ways that will guarantee that they'll be valid categories. In the next video, I began to introduce some of the constructs that exist in any category. I will informally introduce duality and the opposite category, and the concepts of limits and colimits, which we will collectively call universal mapping properties in S. We'll define two in the next video. The initial object, it's only fair that should be first, and the terminal object, which we most certainly don't want to leave for last, as it is amazingly simple but astonishingly useful. We will turn to this object more than any other as we proceed through exploring S. So, see you next time.